Good morning. So this video is going to go through what we do with the second assignment in a little bit more detail. Hopefully most of you have got started with this by now, and as you will know, there's already a video up that takes you step by step through the first part. So once you've done that, and also you should have worked through the tutorials and you've done the exercises in the tutorials, hopefully you've got a fairly good idea about how things work. So I'm just going to have a look at original vice drawings, the document here. If you don't see that, just make sure that you're on tmc.onshape.com and not cad.onshape.com. Okay, and just check that in your address bar if you don't see the documents. So we'll just wait for that to load. And you can see we've got tabs along the bottom, which is all the information that you need. We start off with the getting started with Onshape document, just to, if you I can't remember how to do that, well, we can link back to the tutorials. And remember, if you click on it and it says you've got to purchase this, just open the Learning Centre first, just there, before going to navigating Onshape. So what else do we have down at the bottom here? We've got the actual assignment, which is just loading up now, and that tells us that we've got to do 3D models of all the components. They can be found on the Perl trees, and they can be found in the resources tab on the Moodle, and they can be found through the assignment. So that link will take you there as well. It's not the Moodle. I need to change that at some point. It's not the Moodle, it's Teams now. Okay, so but what it does tell you is this is the criteria that we have to hit for you to so we can say you have achieved a distinction. So that's there as well. So for a pass, create a model and drawings of an assembly containing at least 5 products, and create models and drawings of at least 5 3D components from an assembled product, and apply a material to 2 or more components. Right? So 5 parts, add a material to 2. And adding a material is dead easy. I might, if I remember, I'll show you how to do that as well. It's literally a couple of clicks. So M1, produce accurate models and drawings. So I wouldn't, why would you not be producing accurate models and drawings? You're using CAD software that the whole point of doing computer-aided design is that we produce things accurately. So I'd hope that means that we almost automatically get up into the merit. But it does say at least 7 well-orientated components. So the full thing you see here, we've got MD, merit distinction down the bottom here. That takes us up to that 7 components limit. Okay, and then finally we've got refine models and drawings to an international standard of an accurate and well orientated. So we'll be working through this. You'll make mistakes. We'll correct those mistakes. That counts as refinement to me. So that's the assignment. That's where we're going. That's what we're doing. And we're using Onshape for the entirety of this assignment. We're using Onshape for the drawings, for 3D models, and for the drawings. And then the next assignment follows on with more Onshape. So I'll share some documents later in the new year. Once we get back after Christmas, that'll allow people to just carry on with the next assignment. So what we're looking at here, and somebody said to me the other day, well, what do we do with this? These are 2-dimensional pictures. How do we make a 3D model out of that? It's a good question. So what we've got to remember is that what we're looking at here is all the same thing. They're just different sides of the same thing. So we've got here, if we imagine, you can't see my mouse, can we? Let me just pause and see if I can get my mouse to track. No, I'll not be able to find anything. I'm sure it's there somewhere. Right, so let's just zoom in on the part that we're talking about to make it a bit clear. So what we imagine here is that this view on the right of your screen, let's just close that, there we are, is coming out of the page towards us. So we've got maybe something solid coming out of the page towards us, and then we just rotate that to show this view here. So let's just have a look to explain what I mean a little bit more. We've got the drawing done in Onshape, and here we've got the 3-dimensional model. So let's spin that round to there. Yeah, so there we are. That's sticking out of the page towards us, and then we're just rotating it around to the left there for our other view. Okay, and that's all that's happening in that drawing. Just moving it around the paper like that. Okay, and that's it. You know, and part of the skill that you are learning is how to visualize that, how to take these flat two-dimensional drawings and convert them into three-dimensional images. You know, either in your head or then, you know, in a modeling package like this. Because a lot of engineering design is communicated by this type of drawing. So that's part of what we're learning here. So if we just flick back, so that's our first drawing. So hopefully you've managed to make that by following the previous video. But we can just unpack this perhaps a little bit further and answer some questions. So, for example, what are we looking at on screen here? And some people say layers, and some people say dotted lines. But what I'm really asking is, what do these lines represent? We don't put anything on an engineering drawing without a purpose. So what do these lines represent? And what they represent, well, we've got these blue dash 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 lines. Colour doesn't matter, but the dash 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 does. And they're hidden detail lines. So that means that there's something behind the front face that we can't see. Okay, and it goes all the way through this section here. Okay, and we've got a centre line, so that means that it's symmetric. It's symmetric. So we might look for more information. Ah, that's interesting. We've got a circle here. So what does that tell us? We've got a broken circle. We'll come back to that. What that broken circle means. We've got an arrow coming from the circle that says M12. That's also more information that we can use. So when we put all these three things together, the tram lines, the hidden detail, four things. The tram lines, the hidden detail lines, the broken circle, and the M12. What this tells us is that we've got a hole going through this section. We've got a hole. What this tells us is that this is a hole. Yeah, and we can't see it because it's somewhere, you know, that's not at the front of the part, but we've got a hole going through. And there is the hole, and this M12 tells us it's a metric screw thread. That M there stands for metric screw thread. Okay, 12 means it's 12 millimeters in diameter, and 1.75 is what we call the pitch. So that's the distance from one screw thread to the next screw thread. Yeah, so we're talking about a hole that you can screw something into. That's what we mean by screw thread. Okay, and this broken circle here represents that screw thread. So if you imagine we're looking at the end of a hole, we'd see the screw thread go round and then disappear underneath itself, and that's how we represent that by this broken circle. And it's also how we represent looking at a screw or a screw thread on its side is with these tram lines. If you imagine you look at a screw on its side, we'd have to go zigzag, 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 but life's too short. So where the zigzags would be, we just put these tram lines, and that represents a screw thread. So let's just translate that into 3 dimensions to perhaps understand what's going on a little bit more. So there's our hole look, and we've set that up with the hole button over here to have the detail on it that says yes, this is an M12 hole. But you know, if we then, so there we are. There's our view with the hole, and then as we move that way, yeah, obviously we can't see the hole because we're looking at the front, but the hole is hidden detail. Yeah, so we're looking at a cylindrical shape, so it's a circle there, and then as we move it round, it becomes a rectangle. Okay, so that's what we're looking at. Oopsie daisy. That's what we're looking at when we see this, and part of that comes with experience, you know, of identifying what's going on. Yeah, these are the blue dotted lines at the bottom here represent what we can see, this cut. Yeah, so this cut goes all the way along, and that's what we can see there. So again, let's just, if we go here, we can say shaded with hidden edges. Let's have a look at that. Yeah, so there we go. Yeah, and then there's our view. Let's press the button. There's our view, and then let's take it this way. Yeah, you can see how those hidden detail lines come about there. Okay, so that's how we interpret that drawing. Other things people have asked is, and it's a good question, what is that 1.6 next to the triangle? That 1.6 next to the triangle specifies a surface finish. Essentially how shiny, how smooth, how polished is that surface. So we're looking at that vertical surface that kind of continues at the end of the green line. Let's get rid of that hidden detail a moment, because that's a little bit confusing. So we're looking at that surface there and that surface there. And we specify those on the drawing to be 1.6. That's 1.6 micrometers surface finish, which means that we're saying that has to be smoother than the rest of the part. And we're saying that because we're going to drop the vice, the sliding jaw. There we are. That's the word I'm looking for. The sliding jaw will sit between those two faces and has to slide backwards and forwards nice and smoothly. So we're specifying a better surface finish for those two faces than we're specifying so a smoother surface finish for those two faces of the part than we are for the rest of the model. Okay, so I think that's the important parts from there. So let's have a look at the next drawing and see what we can pull up from there. Here we go. So let's just flick that closed. So again, what are we looking at here? Well, on this view, we're looking at something that comes out of the page and is that shape. Sort of if you imagine a solid block coming out of the page, and then we're just moving it to the left. So we're moving it around, just like some of us did with we did that exercise with our phones right back at the start of the year, where we put our phones on the piece of paper and we moved our phone around the piece of paper without lifting it off, and we maybe just shuffled it around a bit, and then we drew what we saw, and what we found was that the top view was at the bottom and the bottom view was at the top, and the left was on the right and the right was on the left, first angle orthographic projection. I don't know if you remember that, but we did do it for those of you that were on the course at the time. So again, we've got these numbers here, 1.6. So that's for those vertical surfaces. There, because that's slotting into that slot that we just looked at. And the other thing that we've got here is it says 15F7. So when we have holes and things that go in holes, we can have a loose fit, we can have a sliding fit, or we can have a tight fit where the shaft that goes in the hole is actually bigger than the hole, and we do that when we don't want the two parts moving or coming apart again. And we have tolerances for those holes and fits, and so F7 is a specific tolerance, that we work to for that. So that means that'll be a nice fit, so it will slide backwards and forwards nicely within the slot that we just looked at. What do I mean by tolerances? So we can't make anything exactly. Even with a CNC machine, we might be 0.01 of a millimeter, 0.001 of a millimeter if we go slowly. But we still can't make something exactly. We can make it, pretty accurate, but we can't make something exactly. So, for example, this part here is 50 long, and we can't make it exactly 50. So we put a tolerance on our parts, and we say, okay, so the tolerance on this part might be plus or minus 0.5 millimeters. So anything from 49.5 millimeters to 50.5 millimeters, if we measure it anywhere between those two, would be acceptable. And so that's our tolerance. So that'd be a tolerance of a millimeter, plus or minus half a millimeter. And when we're manufacturing, the tighter we make a tolerance, the more expensive it becomes, because that means we need to spend more time on processing, more time on finishing, more time on manufacture. And the more time we spend on something, the more money it costs. As I'm sure I've said to you all before, it is about the money, money, money. It's not about making the world dance. So if we don't have to specify a tight tolerance on something, don't specify a tight tolerance on something. If this can be plus or minus half a millimetre, let's leave it at plus or minus half a millimetre. Okay. If it has to be more accurate, then we'll make it more accurate. But we only make things more accurate when we have to. Okay. So the other thing that you might want to look at is what are we looking at with these blue dotted. So again, we're looking at some hidden detail. We've got tram lines. So we just said that tram lines screw thread. So we've got screw thread, we've got hidden detail, we've got this little triangular thing. Well, if it's hidden detail, we've got tram lines, it's in both views. Maybe we're thinking it's a hole. Right. So what manufacturing process do we use to make holes in steel? We use a drill. So this triangle at the top here then is just the shape of the drill. That's all it is, just the shape of the drill, just to show that. And we've got a centre line. This yellow centre line should probably extend the full length of this view to represent that it's a symmetrical part, whereas here it's just showing the symmetry of the hole, because this isn't a symmetrical part, because we've got the chamfer up the top on the top right corner there. So there's a clue then perhaps as to where this hole is positioned. Where in three-dimensional space do we position that hole? What other information do we have about the hole? Well, we're told it's M10 by 1.5. So again, M, metric screw thread, 10 millimeters diameter, 1.5 pitch. And this 17 tells us that the screw thread depth should be 17 millimeters. And you'll notice that the hole depth isn't specified, because we don't actually care. As long as that hole doesn't pop out of the other end, it could be, how deep is this, 35? It could be that we could drill the hole 30 millimeters deep, as long as we can put 17 millimeters of screw thread into the hole. That's all we're really bothered about. That's what's specified, that's what's important. But where do we put it? Well, we've got a centre line there and we've got a centre line there. So let's look at how that works out in 3 dimensions. So here we are with a movable jaw I made earlier. He says, a movable jaw I made earlier. There we go. Now, if I just press P to put the planes on, fantastic. Yeah. Okay. Right, let's take those off again. So what we're saying is, if we're looking at the front view, yeah, we're looking at a line that runs through the centre. So I'm just going to pick that dot to represent our centre line. Okay. And then again, on our other drawing, we can pick our dot in the centre. And so if we imagine that we slice through the middle, none of my planes slice through the middle. Okay, apart from that one, and that's slicing through the wrong way. So if we slice vertically through the middle, yeah, obviously that's not vertical from point to point, in both directions, then that will tell us that that hole goes in the centre of the part. Yeah, we can see that lines up with the centre there, and that lines up with the centre. That lines up with the centre. He says that lines up with the centre there. So our two dots will line up centrally. Yes, there we go. Yeah, and so that's using the information from the drawing. Yeah, so that's our centre lines, and where those centre lines cross, that tells us it's in the centre of that 3-dimensional shape. Okay, and that's hopefully enough to get you going. The other thing that I liked, that I have said before, I think I said that at the start of the last video, is that certainly while you're learning, even after you learn, you're always learning, even after you become more confident with CAD, I would always treat, you need to be thinking about the manufacturing process, always thinking about the manufacturing process. So these, it says, are made of mild steel. So how do we manufacture steel? Well, we start with a solid block of material and then we remove material. It's called a subtractive process. We take away. So I would always start with the solid block of material in CAD over here, and then I would take things away. And you can see, if I just do the rollback there, you can see that that's how I've modeled it. So we start with the full thing, and then there's a sketch to take out these two corners, and then extrude remove, and then we do the chamfer. Chamfers are one of the last processes that you do. They're a finishing process, just to make things look nicer. Yeah, and then we put the hole in. Okay, so always start with the solid block. Always start with your solid block of material. Yeah, if you're designing something 3D printing, then that's an additive process. We're adding to the material all the time. So you might want to model in a different way. But I think while we're starting out using three-dimensional modeling, it's always worth thinking about, how do I manufacture this? It's made of steel, so I'm going to start with a solid block of steel and I'm going to take things off it. So this part, for example, is generally cylindrical, 24 millimeters diameter at its widest, 29 millimeters, 24 millimeters diameter. We can know that because we see the arrow goes from there to the from the top to the bottom, and it passes through the middle points. That must be the diameter. Okay, and looking at our other view, we can see it's 29 millimeters tall. So I would start by extruding a cylinder that's 24 millimeters in diameter by 29. I would then draw another circle of 14 millimeters diameter on an end face of that cylinder, and then I would extrude remove down to this to the 9 millimeters shelf here. Yeah, and then I draw another circle for M10, so 10 millimeter diameter circle, and I would extrude down to this shelf here. Okay, and that's how I do it. We'd start with the solid block and take parts off, and you get a more coherent model, and it's certainly an easier to edit model than you would doing 1, 2, 3 different extrudes and sort of sticking them together. That's the way I'd recommend we tackle this. I think I've waffled for long enough, so I will put up another video that just goes through how we put the dome on something there. Just a quick video that demonstrates that. And is there anything else that kind of crops up? I don't know, but I'll have a look. Okay, so the next video will go through problems and other things that we might have to encounter for the rest of the model. But hopefully between these videos and the tutorial exercises which you've done from Onshape, you shouldn't encounter any problems. All right, thank you very much. Happy Onshaping.